We're going to explore in this video what ionic compounds are, how they're formed, and then what are our naming rules for them. We're going to look at the simple ionic compounds in this video, and then we'll go to the transition metal ionic compounds in the next one. If I look at the periodic table, of course I've got over here, I've got the metals. I've separated out the two types of transition metals. So if I look at a periodic table, I see there's this jagged dividing line here that separates the non-metals from the metals. So the metals are over here, most of the elements are metals, and then the non-metals up in this corner. Metals form positive ions. When they form ions, frequently the metals are neutral, meaning the protons and electrons count is equal, but also frequently they will release some or all of their valence electrons in order to form positive ions. The non-metals, with the exception of these over here, right, these are the noble gases already have that full valence shell, so they don't react with other elements. These other nonmetals will either share electrons to fill their valence shell, or they will add electrons, forming negative ions to fill that valence shell. So, so that's our distinguisher, and I've drawn that jagged line here. So here's our metals. And so let's look at these metals. Now I've separated hydrogen out here. Hydrogen is technically a non-metal. So what's it doing over here with the metals? It has one valence electron. The periodic table is organized by in columns for how many valence electrons they have. So hydrogen has one valence electron. It will sometimes act like a metal, meaning it will get rid of its one valence electron to form H+. It can also, though, add a valence electron and form H- or hydride, but probably most commonly it will share electrons. So that's the one non-metal that's over here on the metals side. Now let's look at the first one over here in the third period, sodium. I've drawn a shell model for sodium over here. It's got 11 protons in the nucleus. It's got its two electrons in the first shell. Second shell is full with 8, and it's just started with the third period. The third shell has just that one valence electron. Very loosely held, as we've seen in previous videos. So this is a very weakly held to the atom, and it tends to leave. So that sodium, what sodium does to have full valence shell is actually empty its valence shell. So now it's left with only 2 full shells. So sodium in nature is found as Na+. That's the most stable form for sodium, is the sodium ion. I have some sodium, neutral sodium, and it's very reactive, and you drop it in water and it can actually explode. So, so sodium is Na+. Because of that low ionization energy, it gets rid of that. The same is true with all of these metals in the first column. You know, so we have Li. Lithium tends to always be Li+. It's not common to find lithium neutral. Same with potassium, and continuing as we go down. So they always do one thing. They get rid of that one valence electron they have. Metals will never, under normal circumstances, get rid of any core electrons. They'll empty that valence shell for these two. They'll empty the valence shell and leave their inner shells full, right? So sodium only forms Na+. It never forms anything other than Na+. Same thing, lithium, potassium, all of these. When they form ions, which they usually do, they will always release only that one valence electron and leave their core shells full. Now, there's a way to show this. When atoms interact with other atoms to form compounds, they do so through their valence electrons. So there's a shorthand. Rather than having to draw this shell model all the time, there's a shorthand way to do it. And so we'll show sodium, one valence electron. Let's give it 1 dot. These are called Lewis structures, right? So it's showing the symbol sodium with its one valence electron. And so this is how we can kind of see how they're going to interact with other atoms. Magnesium, 2 valence electrons. I'm going to put them on 2 different sides. There's 4 sides to the symbol. I'll put them on 2 different parts. I can put it here and here. I can put it on either side. It doesn't matter where, as long as I put them in 2 different parts. Then we have aluminum, 3 valence electrons. We have silicon, 4 valence electrons. And so I'm showing it this way. This will specially use these, so silicon never forms ions. It shares So silicon is there ready to pair up and make 4 different bonds. So we're going to use these a lot more when it gets to covalent bonding. Then phosphorus. Now phosphorus has 5 valence electrons, so we're going to show we've only got 4 sides, so I'm going to pair up one of them. It doesn't matter if I pair up the top or here, which side, but I got a pair and then 3 more. So for 5 valence electrons, sulfur has 6, and so I draw the 6 valence electrons around it. Chlorine is 7. It's almost there, right? 8 is a full shell. Chlorine is 1 away from doing that. So from this Lewis structure, we can say, okay, well, it tends to bring in that 1, and we can fill that shell. Argon is the noble gas in the 3rd period. It has 8 valence electrons. So we show it in the Lewis structure with these 8 valence electrons. Everything, that's the stable arrangement, a full valence shell. So it's very energy favorable. That's where they want to be. And so these Lewis structures are going to help us predicting how these atoms interact with others. So I can erase my periodic table. So we say sodium with that 1 valence electron tends to release that electron. Where does the electron go? It has to go somewhere. It's not just going floating around. Where might it go? It might go to chlorine. I'll go ahead and draw chlorine with its 1 open space there. Where might that electron go? Maybe it goes to a chlorine atom. And that way chlorine is filled. How do we show this with a Lewis structure? Sodium lost its 1. So with the Lewis structure for an ion, I'm going to show it with an Na+. Chlorine has now gained 1. And what we do with the Lewis structure, so well, wait a minute, chlorine only has 7. How come I'm showing 8? Because it added 1. So we'll tend to put brackets like that and put a negative sign. Now that that's happened, I've got a negatively charged chlorine ion, a positively charged sodium ion. Opposite charges attract, and this attraction is very strong. They're going to click together and bond together. So let me redraw it here with them together. So they're going to click together, and that forms a very strong ionic bond. And then what's going to happen is, of course, there's never just one ionic compound just isolated from everything else. What's going to happen is more positives and negatives are going to add and form this big lattice of salt, sodium chloride. Let's use the Lewis structures for a couple more, and then we're going to go for an even more shortcut. Magnesium, 2 valence electrons. It's going to release both, right? In those first 2 columns that we're looking at, we're going to, they always do the same thing, right? They always are going to empty their first shell. So in fact, I need to go back through that. Let me sketch really quickly. I already distinguished that here's hydrogen. It's kind of a little different. Sometimes it's really a nonmetal over here. The other thing that's different is transition metals. And that will be part of the second video. They're a little bit more complicated, but because you know what? They don't actually empty their full valence shell usually. They don't always form the same charge. These 2 columns that we're going to look at first are very predictable. This first column always loses its 1 valence electron that it has to form a single plus ion. The second column will always release both, always, right? It will release both valence electrons to form 2 plus. So these are always 2 plus when they form ions. This column is always 1 plus when they form ions. And then the transition metals are different. They have different naming rules in here. The one I'm going to isolate and say, even though it's in the transition metals section, aluminum, because aluminum always does the same thing. It has 3 valence electrons and it gets rid of all of them. Aluminum will always be 3 plus. When it's an ion, again, a lot of times there's, aluminum cans are neutral aluminum metal, but when it's an ion, aluminum is always 3 plus. Okay, so magnesium has its 2. It needs to get rid of both. What if there's a chlorine atom nearby? Where can those 2 go? Well, so it's going to get rid of them, and this chlorine is happy to take 1, but that's not enough, right? So it still has 1 more to give. What does it need? Another chlorine. So these Lewis structures can help us predict the formula. That's one way. They're really more useful with the sharing of valence electrons, but we can use them for ionic compounds too. So when magnesium reacts with chlorine, what happens? Magnesium releases its 2 electrons to give to chlorine. One goes to one chlorine and the other goes to another. I can show that here. So magnesium has now formed a 2+ ion. Now I've got these negative charges that are strongly attracted. These ionic bonds, the ionic bonds between oppositely charged ions, between the negative non-metal ion and the positive metal ion, these bonds are very, very strong. All ionic compounds are solids at room temp because the bonds are super, super strong. These things need very high temperatures to melt and break those solid bonds. So I get this kind of arrangement. And again, this is going to be built in a big lattice. So for every magnesium, I'm going to need 2 chlorines. Now, how do we write that as a formula? For sodium chloride, when there was just 1 and 1, we write NaCl. We don't write it so 1 to 1. So, and really these formulas are ratios. For the ionic compounds, they're ratios. For every chlorine, for every sodium, there is 1 chlorine. Right, so it's a 1-to-1 ratio. It's not 1 chlorine, 1 sodium kind of bouncing around somewhere. It is this big lattice that has built up in 1-to-1 ratios. And for magnesium chloride, I need 2 chlorines for every magnesium. Magnesium has 2 electrons to give, and so I need 2 chlorines. We write the formula MgCl2. Right, so that means there are 2 chlorines for every 1 magnesium. These little numbers down here are actually ratios. They're showing I need 2 chlorines for every magnesium. That's how this atom is put together. Now, one more thing before we move to our next shortcut away from Lewis structures. Notice that the Lewis structure for fluorine and chlorine are the same. Why? Because they're in the same column. They both have 7 valence electrons. So they look the same, meaning that they will react the same. So that if they're in the same column, they have similar properties. That's why we group them in that same column. So 7 valence electrons for fluorine, 7 for chlorine. And then, so what will fluorine do? If it's got a sodium nearby, it will take that from that electron from sodium and add it to make the F- ion. So sodium chloride and sodium fluoride will have the same basic formula because they will interact 1 for 1. Now let's use that. Well, before I leave that topic, let's just look at this part of the periodic table. Let's look at these nonmetals. Here, of course, are the noble gases, right? The noble gases are inert. They don't react with other compounds. This column right here, we call them the halogens. They all have one thing in common. They have 7 valence electrons. We're ignoring these electrons in this part, so we're really counting 1, 2, skip that middle part, 3, 4, 5, 6, 7. So fluorine has 7, chlorine has 7, bromine has 7, iodine has 7. So they all have 7 valence electrons, which means they need to add 1. Which means for all of these guys in here, in this row, the halogens, they will add, when they form ions, when they're not sharing, but when they form ions, they will add 1 valence electron because that's all they need to fill the shell. So fluorine will form Cl minus, so F minus, chlorine will form Cl minus, bromine form I Br minus, and iodine I minus. So we already know if I'm going to form an ionic compound with any of these, they will always add one electron and have a 1 minus charge. In this column, let's see, what do we have? The second column over with oxygen being the top. So in oxygen's group, oxygen, I won't write them all there. What do they have? They have 6 valence electrons. You can count them over from the other. They need to add 1, 2 to have 8 valence electrons or a full shell. So oxygen will always add those 2 when it forms ions. It will add 2 to be oxide or to have a 2 minus charge. And it will always do that when it forms ions. It never forms O negative, right? It's always 2 minus. Sulfur, always 2 minus, right? Selenium, always 2 minus. So in this column, very predictable, they'll add 2. In the nitrogen group, now of course the nitrogen group only has a couple of them there before you get into the metals, nitrogen and phosphorus. 5 valence electrons, nitrogen is always 3 minus when it forms an ion. These things are not ion as common because they tend to share more, but when nitrogen is an ion, it's N3 minus always. Phosphorus, always 3 minus. P3 minus. Okay, let's use that. And I'll sketch a periodic table one more time. So I can use this instead of looking at these electrons and the Lewis structures and watching them fly and figure out, okay, this electron goes here, this electron goes here. There's actually a simpler way to do it. I have these guys are always 1 plus, excluding hydrogen. These guys always 2 plus. And then over here, these are always 1 minus. The next column over, 2 minus, 3 minus. I know what charges they form when they form ions. Therefore, I can predict and use that to determine, okay, well, what is the formula for sodium chloride? Notice what we've done. So when we call it an ionic compound, we put the metal first. Don't change the name of the metal. The non-metal gets changed, the suffix, to IDE. So what would the formula for sodium chloride be? Well, I know sodium's right here in the first one. It always forms Na+. I know the formula for chlorine is Cl minus when it forms an ion. That's called the chloride ion. So chlorine becomes chloride when it becomes an ion. And I can see 1 for 1. Now the other key principle is all compounds are neutral. All compounds are neutral, right? There are no exceptions. Every compound must be neutral. So single plus, single minus, the pluses and minus cancel without having to do any kind of multiplying. What is the formula for sodium chloride? NaCl. And so I can simply use the charges that I know they form to figure out the formula. The one I had done with the Lewis structure, I did magnesium. Let's just change it to fluoride. Can't believe I left the O out. Magnesium fluoride, magnesium, I don't even have to look at the valence electrons and watch them go. I can say, well, magnesium's right here. It's always 2 plus when it forms an ion. If it's going to react with fluorine to become fluoride, fluoride is always F minus, -1. What do I need to do to make this work? All compounds are neutral. I've got a 2 plus, I only have a single minus. How do I make it neutral? Add another fluorine. 2 plus, 1, 2. 2 minus, magnesium fluoride has the formula MgF2. Okay, let's do a couple more to show how this works. And then we're going to practice it. Sodium oxide. Oxygen becomes oxide when it adds its 2 electrons. So when oxygen becomes an ion, it is O2 minus, and we call it oxide. Sodium is Na plus. 2 minus, single plus. I need another sodium to make this neutral. Right now I got 1, 2 plus. 2 minus, Na. I need 2 sodiums for every oxide. And again, sodium oxide is this compound, this solid, that builds this big array. How does it build this big array? It has 2 sodium ions for every 1 oxide, Na2O. So metal first and non-metal second. Let's try a couple with aluminum. So the other one we said that is common is right in here. Aluminum always forms 3+. Aluminum bromide. Aluminum's always 3+. Bromine is right in here. Bromine becomes bromide when it adds an electron to become an ion. And it always will add 1. It has 7 valence electrons. It adds 1 to have 8. I need this compound to be neutral. 3+, only a single minus. I need 1, 2, 3. So AlBr3. When you're writing these formulas, be careful. So make sure that aluminum looks like, so I always make it like this. It's tricky if I get to like iodine, I always write like this. So make sure this is not aluminum, some A, looks like an I, AlBr3. So we're going to be careful when we write these formulas so we're not confusing, say, a lowercase l with a capital I or something like that. Okay, one more with aluminum. Okay, so let's look at this one and then say, okay, let's make this neutral. Well, I got too much positive, I need more negative, O2 minus. I got too much negative now, I need more positive, Al3 plus. Oh, and now I got too much positive, not enough negative, add more negative, O2 minus. So what has happened? So now I got 2, 4, 6 negatives, 3 and 6 positives. That makes it neutral. So how did I have to combine these ions to make it a neutral compound? I needed 2 aluminums and 3 oxides. Aluminum oxide, Al2O3, which means it builds in a big compound where there are 2 aluminums for every 3 oxide. That way it's neutral. So we're going to practice this a little bit more with the Google Docs and just practices. These are the simple ones. Just use the charges. Figure out what the charges are. Combine those in ratios that makes it come out so the charges cancel.